So this video is going to go into the modern quantum mechanical model of the atom. And when we get to atoms that have more than one electron, things get just a little bit more complicated. When you're dealing with a hydrogen atom that only has one electron, a lot of this becomes pretty straightforward. And basically this theory will collapse back down into Bohr's model again, except again that we don't think of electrons as orbiting the nucleus exactly. But beyond that, it will sort of collapse back down into Bohr's model if you just have one electron. But most atoms have more than one electron, so this is why we need a more complete, more complex, more comprehensive theory. So what we know is that electrons exist within an atom with different quantum energies. And again, this idea persists from Bohr's model, but we're not just going to assign each electron an n value. It's going to be a little more complicated than that. The energy state of an electron actually has 4 components. And the analogy that I like to use here is, think about your postal address. When someone wants to send you a letter, they need to get the state that you live in and the city, which again the postal service will try to combine these together into a zip code, and that's fine. But you also need to know what street you live on and your house number. And so when we're assigning energies to electrons, we have to think about the components of its sort of electron address, if we want to think of it that way. And so every address has a specific energy associated with it. So let's go through each of the 4 components, and then we'll kind of go back and see how it all fits together. So we'll look at each component individually first, and then we'll see kind of the bigger picture and how everything fits. So number 1 is the energy level. This basically comes straight from Bohr's model. This is the part that's the same. And so the energy level is just going to be a number. We still use the letter n to represent it. And what this basically tells us is an average distance from the nucleus. So as n increases, the electrons are going to gain energy and move further from the nucleus, but not necessarily in these perfect orbits like Bohr's model suggests. So we're not going to draw pictures of exactly how far they are. But in general, an n equals 2 electron has more energy and on average is further from the nucleus than an n equals 1. The next component is the sublevel. And again, Bohr's model does not have any of these other parts, so this is where it gets a little more complicated. But as we move further and further from the nucleus, each of these energy levels becomes bigger, physically bigger, a larger region of space. And so each energy level then becomes more complex. What we find is that each energy level contains n sublevels, where n is equal to the energy level. So when n equals 1, there is only one sublevel. When n equals 2, there are 2 sublevels. When n equals 5, there are 5 sublevels. So it gets more complicated the further from the nucleus that you go. The sublevels are identified with letters. The only 4 that you need to know are the first 4, S, P, D, and F. In the first energy level, we only have S, because when n equals 1, you can only have one sublevel. So we just get S in the first level. In the second level, we get S and P. In the third level, we get S, P, and D. In the fourth energy level, we get S, P, D, and F. In the fifth energy level, we get S, P, D, and F, and additionally we get more, but we're not going to go any further than that. So in the fifth energy level, there are 5 sublevels, but you only need to know the first 4, S, P, D, and F. In the 7th energy level, there are 7 sublevels, but you only need to know the first 4, S, P, D, and F. So hopefully that makes sense, and we'll come back to this idea if not. The third thing that we need to understand is this idea of orbitals. Now, I kind of wish we hadn't chosen this term because, again, we are not talking about the electron orbiting the nucleus. This is a different word, not orbit, but orbital. Different word. And what this is it's a 3-dimensional region of space that contains high electron probability. So we're going to, again, Heisenberg's uncertainty principle has taught us that we can't pinpoint where an electron is at any given instant. But what we're going to discuss is, where do the electrons spend most of their time? Where are they likely to be hanging out at a given instant? And so these are going to be basically pictures. These are shapes, and we'll see all those shapes on the next page. But these are the different regions of space where electrons like to sort of hang out. There's nothing that means they have to be contained within an orbital, within this three-dimensional region of space. The electrons can jump in and out of orbitals, go whereas they please, but if you took lots of pictures of an atom, if you had an electron camera that could actually take pictures and pinpoint where these are, if we took enough pictures, most of the pictures would have the electrons in these orbitals. And then the final component to the energy of an electron is its spin. Every electron within an atom has a spin which is related to its magnetic properties. Basically, scientists have determined there are two possible opposite spins, and we've chosen to call them up and down. Now, those words are completely arbitrary. We could have gone with left and right, or forward and backward, or black and white, or come up with any two opposite terms that you want to relate to these. But if you want to think of it as an actual spin, like a basketball spinning on the end of someone's finger or something, I guess you can do that. But again, it has to do with the magnetic character, and we'll talk a little more about magnetism as we go. So those are the four components of our electron energy. So how does this all fit together? Well, in the first energy level, as we said, there is only one sublevel, and we're going to call it S. Now, there's a mathematical pattern to how many orbitals you get within each sublevel, and it goes by odd numbers. So the first odd number is 1, and so since we're in the first energy level, the first sublevel, we're going to have one orbital, and since there's only one thing here, then we're only going to have one orbital total, right? There's one orbital in that S sublevel, one orbital total for the whole thing. The next piece of the puzzle is that you can have two electrons that are assigned to that orbital as long as their spins are opposite, and we'll get into that more in the subsequent pages as well. So we can put two electrons into that orbital and into that sublevel, which means the total number of electrons that I can have in the first energy level is 2. If I move to the second energy level, I can now have not only an S, but I can have a P as well. Because again, in the second energy level, you can have two sublevels. Again, the number of orbitals goes by odd numbers. So S can hold 3 orbitals. A P sublevel consists of 3 orbitals. So 1 orbital for S, 3 orbitals for P. If I add those together, I get a total of 4. Now again, each orbital can be assigned up to 2 electrons, as long as the spins are opposite. So my S sublevel, since it only has 1 orbital, can hold 2 electrons. My P can hold 6 electrons, because there are 3 orbitals. 3 orbitals times 2 electrons each gives me a total of 6. If I add those together, it means I have a total of 8 electrons that I can put in that second energy level. The pattern keeps going. In the third energy level, I can now have S, P, and D. The number of orbitals, again, always goes by odd numbers. So 1 for S, 3 orbitals for P, 5 orbitals for D. If I add those together, that's a total of 9 orbitals in the third energy level. Every orbital can have 2 electrons assigned to it. So, since there's 1 orbital in the S, that's 2 electrons total. 3 orbitals in the P times 2 is 6 electrons total. And 5 orbitals in the D, 10 electrons. So we're just multiplying that third column over there by 2. And if I add all that together, 2, 6, and 10 gives me 18. And finally, for the fourth energy level, I can have S, I can have P, I can have D, and I can have F. If I look at the pattern, 1, 3, 5, and 7 orbitals in each of those sublevels respectively. So that's a grand total of 16. Again, if I double if I double my odd numbers, I get 2, 6, 10, and 14. That represents the maximum capacity of electrons that can be in each of those sublevels for a grand total of 32. Now, what we said practically is that's all we're ever going to use. So, energy levels 5 and up have more orbitals and max number of electrons, but we will only use S, P, D, and F. So we are never going to use more than 16 orbitals or ever put more than 32 electrons into an energy level. Now theoretically, you might recognize a pattern here. 1, 4, 9, 16. Those are your first four perfect squares. And so the formula actually is that in the energy level n, you will have n squared total orbitals theoretically. And since every orbital can hold 2 electrons, we will get 2 n squared electrons. So that's our mathematical pattern. So for example, if n equals 7, theoretically I could have 49 orbitals and 98 electrons. But in practice, I'm only ever going to use 16 of those orbitals, and I'm never going to put more than 32 in. And so we'll see kind of why that happens as we go along. So this last row here in the chart represents the theoretical number of orbitals and electrons that a given energy level can hold. Again, we're never going to exceed the 16 orbital, 32 electron capacity because we're never going to use any more than the first 4 energy levels. I'm going to stop this segment of the video just to break it up into smaller chunks, but we'll get to more of this on the next page.